Hi everyone. Today we will cover an example of bootstrapping which is commonly used to estimate the sampling distribution of an observed statistic using random sampling methods. We will discover bootstrapping through a simulated coding scenario. This method is extremely important and versatile since we do not have to know the underlying distribution for bootstrapping to work. Instead, we try to estimate that using resampling strategy. In this slide, I'm first simulating data that we will use throughout the presentation. This data is simulated to have an explanatory variable x and an outcome variable y, which is a function of x and noise that is randomly generated using the rnorm function. Lastly, I'm creating a data frame object by binding the x and y attributes. Once the data from the previous slide is simulated, we can look at the head of the data, which is the first 6 observations, and observe the x and y variables. We can always also observe the tail of the data to look at the last 6 observations. So here the x variable ranges from 1 to 10, while the y variable is constructed to be a function of x and random noise. Our goal in this video will be to create a sampling distribution of the beta estimates slopes for variable x from a simple linear regression model. I'm first creating a simple linear regression model using the original data. Here we get a slope estimate of 4.2376 on the x variable, which suggests that an increase in x variable by 1 unit results in an increase in the outcome by about 4.2376 units. This variable is also statistically significant at an alpha level of 0.05. Lastly, we can interpret metrics such as multiple r squared, which is approximately 0.9687. This r squared metric suggests that approximately 96.9% of the variation in the outcome variable is captured by the explanatory variable x. In this slide, I'm plotting a scatter plot of the x and y variables and the regression outcome from the last slide. The explanatory variable is plotted on the x-axis, while the outcome variable is plotted on the y-axis. Here, we observe a linear relationship between the x and y variables based on the line of best fit. In the ggplot function, we first specify the data object that contains the x and y attributes. We then pass both x and y variables in the aesthetics layers, specify a geom point size of 0.8, and add a smoothing best fit line without the standard errors via the geom smooth functionality. This slide is important since it shows an example bootstrap model that we will apply about 5,000 times in the next slide. In this particular slide, I share the general bootstrap framework, which consists of resampling from the originally simulated data by taking a random subsample consisting of the same size as the total number of observations in the data frame. In this case, we are sampling with replacement, which is the essence of bootstrapping. Then we are constructing a linear regression model using the bootstrapped sample. Following the construction of the linear regression model, we are extracting the beta coefficient estimate and the standard error from the summary and the coefficients object corresponding to the x explanatory variable. Here I am visualizing a plot of y versus x, just like the plot from the slide ago. We can see that this plot is less densely populated than the previous plot. This is because we are sampling with replacement. Sampling with replacement means that some observations may be sampled multiple times, which results in overlap in points, thereby giving the impression that the plot is less densely populated. Here we are actually performing the bootstrap operation in this slide by running our code from the previous bootstrap framework slide about 5,000 times using a for loop. In each iteration of the for loop, we sample with replacement, constructing a linear regression model and extracting the beta coefficient from the summary object computed on the simple linear regression model. We are storing the beta estimates in an array object called the bootstrap.slope. After this operation, we will have 5,000 individually values populated in the bootstrap.slope object. In this slide here, I'm showing the sampling distribution of the slopes or the beta estimates associated with the 5,000 bootstrap linear regression models. We can see that the distribution of the bootstrap slope distribution is approximately normally distributed. In the next slide, I will cover how to use this distribution and the standard error to compute the confidence interval. Here we are finally computing the confidence interval associated with the bootstrapped estimates. The standard.error.slope parameter is defined to be the standard deviation of the bootstrap distribution from the previous slide. In this slide, I am also extracting the original slope from the first linear regression model, constructed using the unbootstrapped sample from the original simulation model. Here we get a 95% confidence interval that ranges from 4.194 to 4.281. I hope that this video is of use to you and plan to see you in the next one. Thank you for watching.